Now let's talk about outliers and influential observations. We've already talked about outliers, but in different contexts. But very generally, an outlier is a data point that lies far from the trend of the other points. These points typically have large residuals when we're talking about regression. Now let's go back and revisit what kinds of outliers we've seen before. For example, if I were to make a histogram of heights in inches of a bunch of students, you can see that the vast majority of the students have heights somewhere between, say, 48 and 80 inches or so. They're all clustered right in here. Quite a few are right in here between 60 and 72, in fact. And you can use the empirical rule to sort of guess at about where the middle 68% is and where the middle 95% is and so on. But just by visually inspecting this graph, I can say, oh, guess what? These folks out here are outliers, and these folks out here are outliers. These observations, these height measurements are outliers. And by looking at the y-scaling here, I can see that, oh, there's probably just one there and just one over there. Or I could get a little fancier and calculate the standard deviation for all these heights and see how many standard deviations out from the mean this value is and how many standard deviations out from the mean this value is. And when I do that, that would be computing their z-scores. And I would very likely find that their z-scores were like at least 3 or 4 or 5. This one over here would have a z-score that's probably like +5, and this one over here would probably have a z-score that's somewhere around -3 because it's about 3 standard deviations below average. Another way to detect outliers is with a box plot. Here I've made box plots for shoe sizes of all the students by gender. So shoe size for the women and shoe sizes for the men. And remember, we can use that 1.5 times the interquartile range rule to identify outliers this way. And that's what Minitab is doing here when it identifies these outliers with the stars. That's exactly how it has done that. Okay, so those are potential outliers. The strange thing with regression now is that you have two variables interacting with each other. So suppose I have a data point pattern like this. I don't really see many or any points that are outside of the trend. The trend looks to be, sort of down like this, right? That's sort of, if I were to drop a regression line on there, it would probably look something like that. Now, what if there was another point sort of, say, over here? And maybe we'll color it red just so that we can identify it easily. This point I might consider to be an outlier because it's sort of farther out from the trend, farther out away from the rest of the pack, right? But here's the interesting thing. If you look at this value purely along the x scale this way, like if you were to just consider the x values of all these points, if you were to let them all drop down and situate themselves right there on the x-axis so that you just had, say, like a dot plot there on the x-axis, and this one too, the red one is going to fall down right in here, which is not so strange, okay? These others will fall down this way. Okay, the red one falls right in there, which is not so far from the middle of the pack. On the other hand, if you let all these data values fall to the vertical axis like this, so that you just track their y variable values, guess what? You get the same kind of thing. That is, that the y value for that red data point is not actually so strange with respect to the rest of the pack there. So the interesting thing here is that marginally, or that is, with respect to each of these two variables, the x variable and the y variable here, by themselves, this red data point is not so strange. However, when I look at it this way, when I make a scatter plot this way, it's sort of far out away from the rest of the data points, or far out away from the trend of the rest of the data points. So how do we identify outliers? Well, probably the very best way, if you can, is just to make a scatter plot like this and go, hey, look, there's an outlier. Okay? However, it's not always that easy, especially if you start getting into regression where you have more than one predictor variable. Then it becomes impossible to visualize and impossible to construct graphs that we can see. So we need some kind of way to help us identify outliers. And typically what we do is we look for points that have large residuals. To see the residuals easily is to make a residual plot, and we'll do that. What a residual plot effectively does is takes all the y values of the data points and subtracts the y hat values, or the line, or the values on the line. When you do that, for example, when you take this value for this data point here and subtract its y hat value, which is directly below it on the line, then you get that much. And so that is the residual for that point. What's the residual for this point, however? For the red point? Oh my goodness. It's that much. Look, much larger than any of the others. So in the context of regression, that's one way that we can certainly try to identify outliers. Influential observations are related but different. An influential observation is a data point whose removal from the set will considerably change the regression line. So I tell you what, let's take a look at this with an example. So the following are ages, A, we'll let that be short for age, and years and prices, P. for price, and $100 bills of 12 Corvettes. My units here are $100 bills because otherwise I'd have to put 2 more zeros on each one of these numbers, and then all the stuff wouldn't fit here on the slide. So I've done that for convenience. So first thing I'm going to do is I'm going to try to identify which one of these variables should be my x variable and which should be my y. That is, what should be my independent, what should be my response. What's the natural thing to do? Try to predict the price based on age. So I'm going to say age is my x variable and price is my y variable. Age is my x and price is my y. Okay, I'll pull out my calculator and I'll put these data values into the corresponding lists. I'll put the ages in list 1 and the prices in list 2. So I've done that. Put my ages into list 1 here and my prices into list 2. We'll double check to make sure that you do it right, because if you don't do it right, then it'll be wrong. Everything will be wrong. R will be wrong, R squared will be wrong, whatever that is. Your regression coefficients will be wrong. Wrong, wrong, wrong. Okay, everything will be wrong. So definitely double check. So now I want to get my regression line, so I press stat. Then arrow over to the calc menu because I want to calculate. Go down to option 4 for linear regression. Okay. And my X list is list 1, good. My Y list is list 2, okay. I don't have a frequency list. I do want to store the regression line equation so that I can see it on the graph, right? So I'll press vars, Y vars, enter, enter, okay. I'm going to store that regression equation. That response is going to be called Y1, and I'm going to calculate it. Bang, there we go, very good. So I'm going to write this regression line equation on my notepad here. So what do I have? It looks like my slope is negative 27.1503. Price hat is negative 27.1503. And what are the units on that? Remember, slope gets rise units, which is $100 bills. So I'm going to put times $100 per year, right? And then my predictor variable is age, which has units of years. If you're uncomfortable with those things, remember this is your response, y hat, this is your predictor variable or independent variable, which is your x. And then what's my intercept? 440.9804 approximately. And my intercept also has units of $100 bills. It's easy for me to see how to get the units because over here I have a term and over here I have a term, and these two terms add together to give me something that has units of dollars. So altogether this term has to wind up having units of hundreds of dollars, and this term by itself has to have units of hundreds of dollars. So that means it's real easy to know what the units are for this term. It's $100 bills, right? Same as this thing over here, same as the price. Since this whole thing has to have units of $100 bills and age has units of years, then I need to divide by years here to cancel with the years in the age variable, and also slap a $100 bill on there so we get the right units in the end. Okay, so let's interpret the y-intercept and the slope. The y-intercept, real quick, that's so what that says is that if the age is 0, gosh, when is the age 0? The age is 0 when the car is brand new, right? So for a brand new Corvette, I should expect to pay about 441 $100 bills, or $44,098, something like that, for a brand new Corvette. And then what does the slope mean? It says that essentially what we're observing is that if in fact our data are truly adhering to a linear fit, then it looks like these Corvettes are depreciating in value at a rate of $2,715 per year. All right, real good. And what's my R value? My R value there is negative 0.92547. Okay, so it's pretty good, fairly close to -1. And remember, your R value and your slope will always have the same sign. They're both negative. But R, it's pretty, like I said, it's pretty close to 1 in magnitude, which indicates that the clustering of the data points is fairly linear. When I make a graph of this, and that's what I'm going to do next, I should see a pretty linear trend. So to do that, remember you go to second and stat plot, go into one of the plots. I'll go into plot number 1. Make sure that it's on. If it's off, it'll look like this, okay? So arrow over to on and press enter, and then I want to make a scatter plot, so I go into there, scatter plot, choose the scatter plot icon. List 1 is my X list, list 2 is my Y list, and I like the plus sign for the mark. And so finally, zoom 9. We'll zoom in on a statistical plot. And so there we go. Okay, good. These are all my data points. These points up in here are the newer Corvettes, and they're priced higher. These points down here are the older ones, and they're priced lower. Now, if you had to pick exactly one, just one of these observations to be a potential outlier, which one would it be? Can you tell just by looking at the picture? Remember, it should be the one with the largest residual. Hey, I think it's this one right here, isn't it? Look, the distance, the vertical distance from this point to the line, straight up and down, is larger than any of the other vertical distances. Those are called residuals, right? The residuals are those vertical distances off the line. And this one right here has the largest one. I can hit the trace key and then use the arrow keys to bounce around those points and see which observation that is. There it is. 5-year-old Corvette, $36,200 is what that is. It seems to be priced a little bit high with respect to the other ones. Okay, so this is how you can identify good opportunities to purchase sometimes if you're in the buying and selling business. Okay, I would not buy that car. On the other hand, if you made an observation of, if there was a Corvette down here somewhere, oh my goodness, maybe you should go buy that one and then resell it for this much. Of course, there are other factors at play here. It may be that this Corvette here needs a lot of work, or maybe it was used in an awful crime, or maybe it's hot or something. There's certainly more factors than age that go into determining a fair price for an automobile. Things like mileage, whether or not it was driven a lot in the snow, all kinds of things. Now, what about influential observations? Influential observations are data points whose removal from the data set will considerably change the regression line. Now, if I look in here, I don't know that there are any influential observations. Oftentimes, outliers can be influential, but they don't have to be. Let's think about this for a second. What would happen if I removed this data point from the data set? What kind of an effect would that have on the regression line? Well, I predict the regression line would swing this way just a little bit, right? But probably not a lot, because I can look at the rest of this data point cluster here and see that if I removed this data point from the set, the new regression line is probably just going to go right down in that way. It's not going to change a whole lot. Another way to think about that is that each of these points is tethered to the line by its residual. It sort of tugs on the line through its residual. So if I were to come in here with a pair of scissors and cut that tether, then that allows the line to have some more freedom, and it swings down to get closer to these other points down here. But I predict that by doing that, it's not going to change the regression line considerably. At any rate, let's try that and see what happens. To do that, I'm going to go into my calculator, and I'm going to try this. I'm going to set, just for fun, let's set list 3 equal to list 1. And then I'll go in here to list 4 and set list 4 equal to list 2. Okay, so I've just made a copy of my data set. Okay, you'll see why we're doing this in a minute. What were the coordinates of that outlier? It was the point at 5 years, 362. Right? 36,200. So I tell you what, in list 3 and 4 then, I'm going to delete the coordinates of that point. So I'll delete that 5, and I'll go over here to the right and delete that 362. Okay? Now what I'm going to do is I'm going to do regression on lists 3 and 4, but I'm going to store it very carefully in a different y value so that I can keep both my old and my new lines. So I'll go to Stat, Calc, Regression. Let's see, that's option 4, right? Yeah, and come down here. My X list now is list 3, remember? List 3. My Y list is list 4, and no frequency list. Store my regression equation. I got to be careful here too. Vars, Y vars, enter, but now let's choose Y2, okay? Because I want to be able to plot both. My slope value is now negative 29 and change. What was it before? It was negative 27 and change. And my y-intercept value is now 443. That hasn't changed much either. Let's take a look at the plots there. Okay, I think all I have to do is hit zoom 9, and there's my first regression line, and there's my second one. Okay, in this window, with respect to these points, those two lines aren't very different. The first line was made using all the data points. The second line was made excluding the one that we have called our outlier. So that's not really an influential observation. Okay, so I'll tell you what, I'm going to go back in here into the y equals. I'm going to delete, or just at least turn off this my second regression line, and just focus on my first one again. Now let's go to Stat. Let's do something interesting though. What in reality happens to the prices of Corvettes as time goes by? Well, they certainly depreciate in value, but only up to a point, right? After 25, 30, 40, 50 years, they start becoming very, very valuable, especially if they're well maintained and everything. Okay, so let's add in another data point. Now, in real life, you don't go adding in data points. Okay, you can't just like willy-nilly start making up data. That doesn't fly, right? You got to go out and collect the data. So here's what I did when you weren't looking, I actually went out and I collected another data point. I found a Corvette, turns out, that was 37 years old, selling for $67,000, right? Remember, my units are $100 bills. Now, let's make a scatter plot of these data values and do regression there. So, hit Stat, Calculate, option 4 for linear regression. List 3 and 4, good, already got that. And store my regression equation again, and let's put it in, say, y3, okay? Vars, yvars, enter y3, okay? We'll leave the other two alone, because we might want to go back and take a look. Okay, whoa! Now my slope has even changed sign. It's now positive. What the heck is going on here? And my y-intercept is 310. What in the world is going on here? Let's take a look at the graph. Zoom 9. Oh, you know what? I'm wondering why my graph window isn't situated right. And the reason is because I've got to go back in here to stat plot and go into this thing. See, I've got it. It's basing the graph window size and location on these two lists. I need to go and tell it to use lists 3 and 4 because there's that one data point that's going to cause the graph window to be a very different size now. Okay, so now if I hit zoom 9, holy smokes, there's my first regression line and there's my second one. Now you can really see what's going on, I think. You see this point? This is an example of an influential observation. That is, if I were to throw this data point out of the data set, we would have this regression line. Influential observations are very important. And in reality, you know, this is not a crazy kind of a data point to think about, right? Because in reality, we know that automobiles do in fact depreciate, and then they start to come up in value, right? They sort of go like this. So maybe in fact what I've got going on here is that, sure, you know, things sometimes look flat close up, you know, in a small space, but if you zoom out, holy smokes, the earth is actually round like a ball, right? If I zoom out on this trend of price versus age for automobiles, maybe we need a different kind of a model. This linear model, straight linear model, is not good. Another thing is what you would really probably want to do if you're really interested in being able to predict price of Corvettes based on their age over, say, you know, ages from 0 to 40 or 50 years. What you really need to do is you need to go and collect some more data points in here, okay, for, you know, ages of 10, 12, 15, 20, 25, and 30 and 35 years, okay, and get some data. And then, you know, it'll probably look something like this. And then what you want to do is, once you get those data points, is try building a different kind of a model. Like, you could go to Stat, Calculate. Instead of linear regression, maybe you do quadratic regression or cubic or quartic. Quadratic regression will just fit a parabola to the data. Okay, cubic regression has cubic terms. Quartic regression has terms that have your predictor variable raised to the 4th power. Okay, so let's take a look at quadratic regression just real quick and just see that it will in fact improve. I'm going to store this one yet into another variable there, say vars, yvars, enter, and y4. Okay, we haven't used that one yet. And calculate. There we go. So this is a different kind of a regression form, right? Now we don't just have ax plus b. We have a constant times a squared term plus another constant times the x term, and then plus just a constant by itself. And then these are the estimates for those constants, okay? And there's something here called r squared, which is the same as the other r squared. Essentially, the higher it is, the sort of closer it comes, the closer the model comes to the data points. Let's take a look at this now. There's my first regression line. There's the regression line with the influential observation. And finally, well, there's the parabola there. Okay, this is the quadratic regression. That's a much better fit, right? But still, we're missing a lot of data right in here. If you were to really do a good study, you should go and try to get some data in that region. Now, let me turn off this last model we made and go back to this plot with just the lines. Here's my question to you. Does this second line come close to all the data points? Yeah, it kind of does. You know, what's the residual here? It's really not very much with respect to all these residuals here off of this line. So the R value that corresponds to this line model is probably not so bad. Let's go back and take a look at it. I don't remember what it was, so I'll just go and get it again real quick. Yeah, 0.765. That's not so bad. And in fact, what if we had made that point even more extreme? Had a 55-year-old Corvette was selling for, say, $75,000. Now let's do regression. What's my R value? Oh, it's even better. It's like 0.85. But I know that line is not a very good line for predicting prices of Corvettes based on their age. Okay, if I hit zoom 9, yeah, look, I mean that line does come pretty close. For some reason I've got two lines in there. Yeah, see, that line does come pretty close to all the points, right? But it is not a good model. Even though you have a high R value or high R squared value, it doesn't necessarily mean that your model is a great one. It means that in some sense your model is coming close to most or close to all the points. Okay, but I know from experience, and I also know from this preliminary model, that it's much better to model these data points over here with a line that goes straight through this away. So you've got to be very careful of that. These R values that are close to positive or negative 1, or R squared values that are close to 1, are not necessarily indications of good models, although a lot of people take them to be so. Okay, so finally, let's go back to our original model. Can we use the regression line to predict the price of a 3.5-year-old Corvette from our original model, the one that we wrote down? Sure. I just take 3.5 and I stick it into that regression line equation, right, which was here. So if I take, so my prediction, or my predicted price, is going to be negative 27.1503, $100 per year, times 3.5 years, plus 44, put a dollar sign there, 098.04, and that comes out to be $34,595 and change. So yeah, so that's not so bad, and we can do that because that's not really extrapolating, right? 3.5 years, that's down and around where we actually made some observations, between like 1 and 6 years or so. But what about trying to price a 55-year-old Corvette? Well, I'll do the same kind of thing, except now I'll just put 55 years in there, and when I do that, I get, whoa, holy smokes, negative $105,228.61. That is, you'd have to pay someone over $100,000 to take that Corvette off your hands. I don't think so. So you can see where our straight line models can oftentimes fall short when you try to make predictions of the response variable based on values of the predictor variable outside of the range of predictor variable values that you've already observed. That's called extrapolation.